Hello dear students, welcome to the classroom point. In today's session we are going to discuss the N-Bromo succinamide. It is also known as the NBS. So let us see the structure of the NBS. This is the structure of the NBS and it is also called the N-Bromo succinamide. Then let us see how to prepare the N-Bromo succinamide. Initially succinamide is subjected with the ice cold bromine. So bromine in the presence of the NaOH at 0 degrees centigrade, it gives N-Bromo succinamide along with the HBr. This HBr is so important in writing the mechanism of the free radical substitution reaction of the N-Bromo succinamide. Most of us know very well about the N-Bromo succinamide as the allylic or benzylic brominating agent, but other than these two reactions, it will do so many other reactions also, so many other important reactions also. Let us see some applications and them also one by one. Initially, let us see the properties of this N-Bromo succinamide. It is an imide family reagent. Imide means C double bond O, NH, C double bond O. The compounds having this type of the group are called the imide family compounds. Okay. And the other thing is, it is a brominating agent. Just now we said it will do free radical substitution of the bromine at allylic as well as the benzylic positions. Wherever allylic or benzylic positions are there it will do the allylic and benzylic free radical substitution reactions. Let us see what does it mean by allylic or benzylic position. You must remember one thing, that this is an sp2 hybridized carbon atom. This is also an sp2 hybridized carbon atom where carbon-carbon are linked by the double bond. And imagine this is then sp3 hybridized carbon atom where there is no double bond. The sp3 carbon atom bonded to an sp2 hybridized carbon atom is called the allylic carbon. Similarly, the carbon connected to the benzene ring is called the benzylic carbon. The sp3 carbon bonded to the benzene ring is called the benzylic carbon. So if any hydrogen is present any of these allylic or benzylic carbon atoms, this N-Bromo succinamide replaces this hydrogen with the bromine free radical, so that we say that it is undergoing the free radical substitution of the bromine. And next one, it is also acting as electrophilic brominating agent and give electrophilic addition reactions also, that we shall discuss. And it is also acting as the oxidizing agent as well as the decarboxylating agent, and it will do substitution of the bromine at the alpha carbon of the ketones having at least one enolic hydrogen atom. Let's see one by one. Initially, what solvents can we use for this N-Bromo succinamide? Why? Because most of these reactions, electrophilic reaction, oxidation reaction, decarboxylating agent, alpha carbon, substitution of the alpha carbon of the ketone, as well as the free radical substitution reactions, they depend on the conditions, reaction conditions. If you change the conditions, the way the reagent act towards a particular substrate also changes. Now, solvents used here are, usually we use carbon tetrachloride as the solvent along with the N-Bromo succinamide and not any other polar solvent like H2O for free radical substitution reaction. But if you want to conduct an electrophilic addition reaction, then we need to use the polar solvents like H2O. So in the presence of the non-polar solvents, it works as the free radical brominating agent. In the presence of the polar solvents, it works as the electrophilic addition reagent. And the purpose of using CCl4 is because there are many non-polar solvents also. Reason is, when N-Bromo succinamide is subjected to works with a substrate, this bromine will be transferred to the substrate and we get the brominated substrate molecule, and later this N-Bromo succinamide will be changed to the succinamide. This succinamide is purely insoluble in the carbon tetrachloride, and it is very lighter than the carbon tetrachloride, hence it floats over the carbon tetrachloride and it becomes easy to separate the compound from the required product. Then let us see how does it work as the electrophilic addition of the brominating agent. if you see the structure of this particular N-Bromo succinamide, there is a lot of electronegative difference between the nitrogen and bromine. Moreover, this nitrogen is connected to 2 electron withdrawing keto groups. Hence, nitrogen bromine bond is completely polarized, so that bromine is the partial negative charge, whereas the nitrogen gets the partial positive charge. That is the reason why, since bromine is getting the partial positive charge, and after getting of this negative charge over the nitrogen, this negative charge will be undergo resonance with this particular double bond O, hence it becomes stabilized. So that is the reason why this N-Bromo succinamide molecule is able to release the bromonium ion Br plus. So once Br plus is released, automatically it will undergo in the bromination reaction, just like our normal bromine with CCl4. See, for this double bond, if we add bromine in the presence of the CCl4, we used to get the intermediate molecule like this, one non-classified cation. So this particular cation, afterwards another bromide ion attacks from the back side, so that we get the vicinal dihalide like this. If it is on the top bromine, this bromine, the next bromine will attack from the back side. And similar procedure also we can see in the case of the N-Bromo succinamide when it works as the electrophilic addition agent. Let us see conditions for free radical bromination reaction. The conditions for the free radical bromination reaction is we must and should provide the radical initiators, like we have to use the sunlight, heat, peroxide, or a radical initiator like AIIMS. This is called as the isobutyronitrile. This is the molecular formula of this particular AIIMS. So these are all conditions are able to generate the free radical. Once a free radical is provided, automatically allylic and benzylic bromination will happen. Now let us see other conditions that are required for the electrophilic bromination reaction. Just now we discussed that N-Bromo succinamide in the presence of the polar solvents like H2O, NaOH, tetraethyl ammonium bromide, it works as the electrophilic addition reagent, not as a free radical brominating agent. So when used these conditions like sunlight, heat, peroxide, radical initiator like AIIMS, then bromination happens at the allylic and benzylic positions, not at the double bond. But when you use these conditions like polar solvents like H2O, NaOH, and this particular tetraethyl ammonium bromide, etc., then bromination happens at the double bond, not at the allylic or benzylic position. Now let us see some of the important substitution reactions. So substitution reaction that takes place at the allylic and benzylic positions with NBS is called the Ohl-Ziegler bromination reaction. So now you must remember one thing, that before discussing this particular reaction, whenever one or more than one allylic or benzylic carbon with hydrogens are there, then you shall get the almost all products, but one must be the major compound. So let us take the cyclohexene molecule. When NBS is used, so this NBS is able to provide the undergo free radical substitution reaction at the allylic carbon atoms. So here two allylic carbon atoms are there. This is one allylic, this is another allylic. So they are same, equivalent, so that whether you put bromine here or here, the molecule will be same. Let us take the another molecule. So in which this is an allylic carbon, because this carbon is connected to the double bonded carbon atom. Similarly, this is an allylic carbon. Okay, so now bromination happens at both the positions, but this is secondary allylic carbon, which is more stable than the primary allylic carbon free radical. Hence, bromination happens at this particular carbon with 68% is a major compound, and this is a 32%. Now, let us take other molecules also. So, in this particular case, let us see how many allylic or benzylic carbon atoms are there. This is an allylic. This is also an allylic carbon atom. But moreover, this is not only allylic, even benzylic, because it is connected to the benzene ring also. So, it is allylic and benzylic. At the same time, tertiary allylic and benzylic carbon. So, tertiary allylic and benzylic radical is more stable than the primary allylic carbon free radical. Hence, bromine NBS will provide the bromination at this particular carbon with 91%. This is only just 9%. at a primary position. Now let us take the another molecule. Here this is one particular carbon. This is benzylic. This is benzylic as well as allylic. This is only allylic, and this is the primary one, and this is the tertiary one. This is the primary one. Primary benzylic, primary allylic, tertiary allylic as well as benzylic. So this is more stable free radical compared to these two. Hence bromination happens at particular this position. In all these reactions I am using NBS CCl4 HNO. You can see HNO, apart from the HNO, you can use other radical initiators also, like peroxide. Here we use in the reaction number 2 like here, but NBS CCl4 is common. Now so here bromination happens and this is the product. And if you take the another molecule like these two, so in this particular condition we are using the AIB, and you can use HNO also, no problem. It is just a radical initiator, so it is a secondary benzylic carbon atom, so that it is more stable free radical, so that bromination happens only at this carbon atom. And this is a 1-methyl naphthalene, and this particular position is a benzylic carbon atom, so that bromine will substitute over this particular hydrogen, so that we get this molecule NBS CCl4 peroxide are the again reagent combination. Now here, now this is not the benzylic, but it is an allylic, because double bond carbon with CH3sp3 hybridized carbon atom is there, so that NBS will substitute bromine at this particular position. Substitute means simple thing that you just remove one hydrogen, put one bromine there, so that we get this particular molecule. Okay. Now let us take another molecule. Most of the people get the doubt regarding whether what about if carboxylic acids, ketones, aldehydes or esters are there, whether the same reaction will happen or not. The same reaction will happen irrespective of the type of the functional group present over these particular reagent combination reactants. So NBS CCl4 peroxide, here this is the only allylic carbon atom, and rest are not the allylic carbon atom, so that bromination happens at this position. So it replaces one of these hydrogen with the bromine. Now let us take this particular molecule. When two equivalents of N-Bromo succinamide is used, the bromination happens at the two positions, not at the one position, so that this product will come. Now the similar compound, but 6-membered ring is there, so that N-Bromo succinamide with CCl4 and HNO when used. So here bromination happens not at this position, but benzylic and allylic, no. So that bromination happens at particular this position. This is directly benzene carbon. Bromination will never happen at the benzene carbon by N-Bromo succinamide, but happens at the only allylic or benzylic position. So this is the benzylic carbon. So you can put the bromine either here or here, both are same. But if you use the two equivalents, then bromination happens here, not there. Now let us see alpha bromination of ketones with enolic hydrogen. So when you take the ketones, it may be cyclic ketone or acyclic ketone, NBS along with the alkali. Here the reaction condition is not the CCl alkali. When you use the alkali, OH minus abstract the enolic hydrogen, because enolic hydrogen is more acidic, so that H plus N comes out. OH minus abstract that H plus N, it will be removed in the form of the water molecule. So these electrons undergo enolization tautomerism. Later the negative charge when comes back, these pi electrons will attack over the positive charge, delta positive charged bromine. This particular molecule we have discussed in the electrophilic addition of the bromination of the N-Bromo succinamide, and these electrons will be shifted over to the nitrogen, so that bromination can easily happen at this alpha position of the ketones. You can take the cyclic ketones also. Now electrophilic addition reactions. So in the case of the electrophilic addition reactions, we don't take the CCl4 along with NBS, we just take the any polar solvent. See here, if you take the NBS with the CCl4 and HNO, then the product would be like this. But when you use the polar solvent, So bromination happens at the double bonded carbon atom like this, just like it's a trans bromination or anti-bromination happens. Just like normal Br2CCl4, same mechanism here we can see. So now NBS with H2O when used, bromine react with the H2O and gives HOBr, so that we get the hydroxybromides. So initially, if the generally question arises among the people that how this trans combination is coming. Let us see here. I'll take this molecule and I'm writing over here. This is the one. After bromination on the double bond, we get non-classified cation like this bromonium cation. So when OH minus ion is approaching, it has to approach from the opposite side. So that it comes over here. So when OH minus ion is approaching from the opposite side, imagine this is coming from the back side. Then OH bromine is on the top side. So that it will be in the both are in the opposite side to each other in this particular molecule. And afterwards, this particular molecule also, epoxide is the final product. Why? Because here neighboring group participation NGP takes place, so that bromine will be removed. So that finally epoxide will be formed. And a similar application was asked in the CSIR 2016 examination. This was the molecule. So in this molecule, when used NBS with 30% NaOH, this is the question. So initially this product happens OH with Br, both are in the opposite side to the molecule. Then neighboring group participation, so the epoxide comes on the top. Why? Because initially bromination happens on the opposite side to this particular tertiary butyl molecule, because this is the upside of the molecule and this is the bottom side of the molecule. Bromination happens later. OH minus, like here, bromination happens later. OH minus ion approaches from the top of the or opposite side to the brominium cation, so that here this bond will break like this, and bromine goes down and OH comes up. So now OH and this tertiary butyl species both are in the same side, so that now this lone pair of electrons attacks over here and removes this bromine. So now oxygen means epoxy part and this part both will be on the same side of the molecule. Here also, this is the molecule carboxylic acid. NBS with alkali when used, initially bromination cyclic adient similar to this one will form. Afterwards, the lone pair of electrons of the CO minus attacks from the opposite side of this type of the cation and opens the ring, so that we get this type of the molecule. Now let us see how this N-Bromo succinamide acts as an oxidizing agent. When primary amines are there, it converts the primary amines to the aldehyde, primary alcohols to the aldehyde, secondary alcohols to the ketone. So whenever these combination compounds are there, then they shall be converted to the respective compounds. So now here primary amine aldehyde, here condition is dark condition. We are not using any polar solvent, non-polar solvent, or radical initiate, anything, only dark conditions. NBS with a dark condition, so the primary alcohol to the aldehyde, secondary alcohol to the ketone. And if to this ketone again NBS with any alkali is used, so bromination happens here. Why? Because that we had discussed already, like this. Again, if you use the NBS with alkali, so that enolic hydrogen is there, hence bromination happens over there. Next, decarboxylation. So NBS also acts as a decarboxylating agent when alpha hydroxycarboxylic acid or alpha aminocarboxylic acids are present. Means to the COH group, if any OH group or NH2 group at the alpha position, in such condition, NBS with H2 and heating combination converts that particular alpha hydroxycarboxylic acids to the aldehyde with the CO2, alpha aminocarboxylic acids to the aldehyde and CO2, finally ammonia will be coming out. So here lactic acid, if you take, this will be removed as a CO2 and this becomes the primary alcohol. This will be oxidized to the aldehyde. And NBS, yes, CO2 and this becomes the primary amine. Again primary amine will be converted to the aldehyde, and these two reactions we have discussed here, the like primary alcohol and primary amine. So hope you like my video and I understood the explanation. If you understand, please like the video and subscribe the channel. Thank you.